Good evening, Internet. I am Matt Buyak, and tonight we'll be tackling the second problem in the projecteuler.net problem archive. In the previous video, we took a look at solving this problem by writing a simple C program, and in this video, we'll attempt to solve it purely through analysis without any programming assistance. So just to recap, the goal of this problem is to find the sum of the even Fibonacci numbers less than 4 million. Now, before we dive into the analysis, let's just take a quick look at the first few terms which they have listed out here. So you'll notice that it's actually every third Fibonacci number is even, and that's not by accident. It has to do with the fact that if you add an even number and an odd number, then you'll get an odd number. And if you add two odd numbers, then you get an even number. And so it creates this pattern of odd, odd, even, odd, odd, even. And so that'll be important when we actually try to solve this formally. So let's get into our terminal here. So we'll start by opening up Emacs and go to our problem directory, which we created in the last video. Open up our analysis file. And the first thing that I want to look up actually is there's a formula for the Fibonacci sequence. Let's see here. Yeah, so this right here. And so this is what we're going to be using to do our analysis, is this expression here. So you might recognize this, this term here as the golden ratio, or phi. And this term over here on the right as being 1 minus phi. And so that this expression can look a little bit intimidating, but if you just think of that as the golden ratio and 1 minus the golden ratio, then I think you'll see that it's being a little bit more manageable. So just real quick, let's copy that over to our analysis file here. So that's going to be what was it? Phi to the n minus 1 minus phi to the n divided by the square root of 5. And we'll say recall that phi is equal to 1 plus square root of 5 over 2. Okay, so we're really only concerned with the every third number. From the problem statement here, we're only adding up the even numbers. Now, one thing that you might have noticed looking at this expression is that if we actually evaluate these, let's take a look at what the 0th Fibonacci number is. That's pretty simple. Both of these are going to end up being 1, and then you have 1 minus 1 is oh, excuse me there. Yeah, 1 minus 1 is 0, and so we have f of 0 is going to be equal to 0. And then if we look at the first Fibonacci number, then again, this is pretty easy to evaluate. You're just going to have phi minus 1 minus phi. Yeah, so we'll just have phi minus 1 minus phi. That's going to be divided by the square root of 5. And so that's going to give us 2 phi minus 1 over square root of 5. And if we look up here at the definition of phi, then you're multiplying that by 2 and subtracting 1 just gives us the square root of 5. And so we end up with square root of 5 over 5, which is equal to 1. So that's what we expect. So continuing on, and the reason why I'm calculating these first few terms is going to become apparent in just a moment. So just bear with me. So then we're going to have this starts to get to the point where we actually have to pull out our calculator here. So let's pull that up, and let's just say 1 plus what we got here, the 5 to the 0.5, and then all that over 2. So that's going to be our golden ratio there, and we'll just save that real quick. And so then to evaluate our expression at 2, we're going to say phi squared minus 1 minus phi squared, and then all of that divided by the square root of 5. So that gives us 1. Again, as expected. Now, you might notice that this differs slightly from the first few terms that they have listed here. They actually have it starting at 1 rather than starting at 0. So we have to be a little bit careful to make sure that our equation actually gives us what we want. And in particular, we'll notice that the first even term is going to be the third term. Or in fact, we can actually include 0 because we're adding over all the values, the even values, and so 0 doesn't change our result. Okay, so we have our expression here. But as I mentioned, we're really only concerned about the even terms, the even Fibonacci numbers. And so what we really want to do is say, we're going to sum from n equals 0 to, at this point we don't know, we'll just say question mark. But then we're going to replace this with 3n. So we're actually only getting every third Fibonacci number. So you can see if you plug in 0, then you get the first term here, 0. And then if you plug in a 1, then you'll get 3, which will give you f of 3, which is 2, which is the next even Fibonacci number. And so we can see that by making this replacement here, this gives us the expression for the sum over the even Fibonacci numbers. Okay, so we can do a little bit of simplification here. So in particular, we can see that let's just copy this. We don't want the Windows menu. Nobody ever wants the Windows menu. Okay, so we can actually factor out this this square root of 5 term because it's going to be the same for every single term. So we can just factor that out. And so then we just have the sum over phi to the 3n minus 1 minus phi to the 3n. Now, this part in here we can then split up into 2 separate sums. So let's say we've got the sum from 0 to question mark of this value here, phi to the 3n. And then we're going to subtract the sum n equals 0 to question mark, question mark, question mark of 1 minus phi to the 3n. So let's just make sure we got our parentheses matching here. Oh, wait a minute. There we go. Okay. And then all of that over the square root of 5. And so now we have these two sums here. And you might recognize these as being geometric series. So if you're not familiar with that, I think it's worth taking just a moment here to go over what that is. So if we have some sum that's of the form 1 plus, actually let's make this a to the 0 plus a to the 1 plus ... plus a to the r minus 1 plus a to the r. So we have some like that. This is a geometric series. And there's actually a nice trick for solving these. You can just look up the equation, but I think it's actually worth going over the actual reasoning for why the formula is what it is. So if we multiply the left and right side of this equation by a, then we're going to bump each of these up by 1. And now we can subtract the top expression here from the bottom, and that's going to give us, let's see, we'll factor out an s there, so a minus 1. And so you'll notice that most of the terms here are going to cancel out. I didn't actually write in all the terms, but here we would have had this a squared, and down here we would have this a to the r minus 1. And so most of these terms here are going to cancel out, which is nice, because instead of having this arbitrarily long sum of terms, almost everything cancels out, and we just end up with this nice expression here where we have a to the r plus 1 minus a to the 0, which is just 1. And then from that we can actually solve for our sum. And there you go. So this is our equation for the sum of a geometric series here, where a is the thing you're multiplying by, and then r is the largest exponent, assuming that we're starting with 0 as our lowest exponent. So if we take a look, let's just look at one part of this when we're summing over phi to the 3n. So that's going to look like, okay, so n starts off at 0, so we're going to have phi to the 0 plus phi to the 3 plus phi to the 6th plus ... So we can see by comparing that to our sum up here that we've got a is equal to, actually this, before I continue here, this maybe warrants a little bit more analysis. So we might be tempted to say a is equal to phi, but that would actually be a mistake, because then you can see we would end up with our second term would be phi to the first, and our third term would be phi squared, which is not actually what we see. So we have to be careful that we're actually multiplying by phi cubed every time. And then r is going to be, well, you know what? Let's we should probably stop calling this a question mark, question mark, question mark, question mark. So we're gonna call this n. So that's going to be the exponent for the largest even number less than 4 million. That's a Fibonacci number. And so we don't know what that will be yet. We're going to have to figure that out. But for now, we're just going to use n as our placeholder. And so you'll notice that this sum goes all the way up to phi cubed to the capital N. And so r is just going to be capital N there. And so that gives us our sum is equal to, we've got phi cubed to the n plus 1 minus 1 divided by phi cubed minus 1. And so we can do a similar bit of analysis for the other sum, which is on 1 minus phi. Yeah, so if we do the same sort of analysis, we come up with mostly the same result. The only difference is that I'll call this maybe S prime just to distinguish them, and we'll just make this 1 minus phi, and same here, we'll have 1 minus phi. Okay, so at this point we're getting closer to the solution. The main thing that we're missing is this value of n. And so what we really need to do is find the Fibonacci number which is even and less than 4 million, but is the greatest such number. So let's pull up our calculator real quick, and maybe we can just make a guess. Let's suppose you may know that the Fibonacci numbers roughly increase exponentially, where the base of the exponent is the golden ratio. And so roughly speaking, it's gonna increase like phi to the x, but that's gonna be less than 2 to the x, and we know that 2 to the x, if 2 to the x is roughly 4 million, then that's roughly 2 to the 22nd. Now, this is one of those things where, as a programmer, you just it's really useful to know the powers of 2. They come up a lot in programming, and so if you do 2 to the 22nd here, that comes up to roughly 4 million. So that might not be a bad place to start. Let's try what's the 22nd Fibonacci number, and in fact, actually, let's add a few to that, because we rounded the exponent up, and so it's let's do 2 to the the 25th Fibonacci number here. So if we recall our expression that we were using up here, then we're going to have let's see, we've got phi to the 25th minus 1 minus phi to the 25th, and that whole thing is going to be divided by 5 to the 1/2. And so that gives us 75,000. So we came up a little bit short. Our estimate wasn't really spot on there. So but that's okay. Now we know that we've got a lower bound. So what if instead we try the 50th Fibonacci number? So we could try that to the 50th minus 1 minus phi to the 50th divided by, let's see here, we got 5 to the 1/2. Okay, so that's quite a bit larger, and so our we know that the term that we're interested in is actually going to be somewhere in the middle. So we can just keep tracking this down. Let's go with, let's say the 35th. I think that's, or let's stick with numbers that are divisible by 3, because it's actually going to be a number divisible by 3 is the one that we're interested in. So we might as well stick to those. So that's going to be phi to the 36th minus 1 minus phi to the 36th divided by 5 to the 1/2. All right, so we're getting closer there, 14 million. So let's maybe go with the 30th Fibonacci number. Let's see here. So we'll do phi to the 30th minus 1 minus phi to the 30th divided by square root of 5. Okay, so it's more than that, but you'll notice we tried the 36th and we tried the 30th. So there's only one more number left in between. And so when we're going to try the 33rd, and if it's greater than 4 million, then we know that the 30th term is actually what we're interested in. And if it's less than 4 million, then it'll be the 33rd term is the one that we're interested in. So let's find out. So phi to the 33rd minus 1 minus phi to the 33rd divided by 5 to the square root of 2. And that's actually less than 4 million. And so now we have our value of n, which is 11. Be careful. It's easy to make the mistake of using 33 instead of 11. So let's just note that down here. So we've got our value of n is equal to 11. All right, so now we can do some calculation to find out what the sum is for, or what s and s prime work out to. Now, just as a reminder, our actual, you can say s actual, is going to be s minus s prime over square root of 5. So let's just recall that that's what how we're going to end up using those two numbers there. The full expression up here is a little bit difficult to parse, and so it can be useful to just rewrite it like that. All right, so let's start off here. We'll just be very careful entering this in. There's a lot of pieces and parts here. So we're going to say phi cubed to the 12th minus 1 gives us that value, divided by phi cubed minus 1. And well, that is quite a mouthful there. Yeah, there we go. I thought that wasn't quite right. Forgot the final enter. So we're going to copy that and paste that into here. And then we're going to do likewise here. Okay, and just to simplify things a little bit, I'm going to grab phi. Let's see here. Yeah, we'll negate that and add 1. So that gives us our 1 minus phi. We're going to clear our memory and then save that, because we don't need the original value of phi anymore. We're just going to be using 1 minus phi. So that's really what we want. Okay, so for s prime, we're going to have, call it phi prime. So we're going to have phi prime cubed. And then we're going to take that to the 12th. Minus 1. And then we have that divided by, call it phi prime cubed minus 1. Gives us 0.089. Oh, that's very interesting. Okay, so then we're going to save that. There we go. We're going to pick this up again. So we're going to take this s prime here and negate that and add seems to be refusing to pay smart. We're going to do this the long, difficult way. Not sure why it. Well, let's try this one more time. Might have to do it this way. It's not letting me copy. I think this has to do with I think it doesn't like me copying out of the Windows subsystem for Linux. So we'll just do things the long and painful way here. Yeah. Okay, so say plus 103.166.19.1909.8302. Yeah, I think we made a mistake here. Something went wrong. 103.16619.190983 minus 0.0901.697 divided by 5 to the 0.5. So that's looks like 4613.732. So we'll copy that. And we know that it's an integer, so we're just going to round that up to 4,613,732. And if we go back to the archive, that's exactly what the answer is. So in the next video, we'll continue with problem number 3. Hope to see you there.